This is the controller tuning process for a tail-seater UAV. Without the controller, the UAV just dangles there oscillating. But now I've turned on the controller and it quickly returns to its desired angular position. So how long do you think it took for me to tune the controller like this? If it were a multi-rotor, it would have taken just a couple of minutes. But for this tail-seater, it took me a couple of months. And yeah, you heard it right. And you might say, that's because you are a bad engineer, Elliot. And honestly, I think that's fair. It even took me a couple of weeks to just write these 5 lines of code. Did I have to learn C++ before I write these 5 lines of code? No, I've been coding C++ since middle school as a classic nerd. So why did it take so long? It's because of this little number right here. Finding that number is what we call system identification, and I cheated by reading the research paper from a team at the University of Toronto. And I didn't even count the days I spent just reading the paper. As I mentioned in another video, robotics engineering is different from the software engineering for the same reason machine learning is different from the traditional programming. Like the coding skills alone are not enough. Often the code in your fancy robot is shorter than you'd expect because most of the work lies in parameters like this number. So what's the difference in between the robotics research and development? In short, the research is about discovering the new algorithms to control the new robots, while the development is taking those research papers and building robots and, well, selling them. Yeah, that was a joke. But the point is that while research and development are closely related, they are not quite the same. Please stick around until the end of this video and you will get a clear idea of whether you want to focus on research, development, or maybe both. So let's dive in. Oh, and if you're new to here, my name is Elliot. I'm a robotics engineer, educator, and entrepreneur providing services related to robotics. Okay, to clarify my point, let me simplify the scenario. In this virtual robot simulation, here's a free-falling object, and we'll assume no air resistance, classic physics 101. And here's the differential equation for the free fall. With a little matrix magic, we can rewrite it in a matrix form like this, and add a couple of lines of control optimization, and voila! You get these tuned parameters for the position and velocity control. Now, with just a few lines of code, you can calculate the total lift needed from the 4 motors to keep the object at the desired altitude. Easy peasy, right? And I'm not skipping any steps. This really is all the code you need for the height control or altitude control, at least in Python. But see this simple linear function here? These similar trivial lines of code in practice would actually take me weeks to implement. Why? Because I had to figure out the number like this. So what is this number? First, the total force required to hover a drone is calculated as its weight plus the thrust to go up at the moment of the takeoff. Divide that force by 4, because there are 4 motors literally, and you get the required force per motor. But here's the tricky part. How do you actually calculate exact force that is calculated by this controller? The key is identifying the relationship between the motor's PWM or pulse width modulation input and its proportion force. PWM is the input signal for the motor. To figure out this relationship, I set up a basic lab with a strain gauge and a 3D printed motor mount, and I measure the proportion force while varying the PWM input. Here's the data I collected. As you can see, the relationship is quadratic. The force increases faster as you increase the motor input. Our goal is to find out the inverse function of this relationship. Why? Because from the main controller, the controller calculated the required force at the moment, and to generate that force, you need to calculate the correct PWM input. The inverse function can be calculated using the quadratic formula, or to simplify, you can approximate it with the square root of the lift and take only the linear part. Feed the data, and finally this is the number came out. Now, this is one of the simpler cases. For the nonlinear systems, fitting the data becomes much harder. For those systems, it's helpful to have frameworks that make the process easier, and that's where the research comes in. For example, Steve Brunton, a professor at the University of Washington, works on the nonlinear system identification using the methods like neural networks. One of his notable contributions is sindy, sparse identification of nonlinear dynamics. Sindy helps identify the governing equations of the system from time series data, representing complex dynamics in a simplified interpretable form, and it appears the sparse regression to a library of candidate functions, selecting only the critical terms that describe the system's behavior. This makes it a powerful tool for the researchers and engineers working with the systems where deriving equations from the first principle is very difficult. What's fascinating about the sindy is its balance between the complexity and simplicity. The traditional approaches like neural networks produce highly accurate models, but they are hard to interpret. Sindy focuses on the sparsity, finding the smallest set of terms to describe the system accurately. For example, in a drone system, Sindy could help uncover the relationships between the motor, thrust, drag, and aerodynamic forces, providing insights which are crucial for controller design and optimization. If you are curious, check out Steve Brunton's YouTube channel. He explains it all really well. Anyway, I'm not that interested in investing my time in building the new cool methods like him, and I'd prefer studying ideas from the research papers like this and applying them to my robots. It's like web development. I don't really create the new NPM packages all the time. I just use existing ones to build my website. Similarly, the research papers are like NPM packages for the robot developers or Python packages. I just use them to build my robot, and that to me is the difference between the robotics research and development. So that's my take on the difference between the robotics research and the development. Both are essential and interconnected. The researchers create the foundational tools and algorithms, while the developers use those tools to build the real-world systems like autonomous drones or robotic arms. But in the other cases, at minimum, you might need to be able to read and implement the research papers. If you're trying to decide between the research and development, ask yourself, do you enjoy pushing the boundaries of what's possible and solving the theoretical problems? Or are you more excited about applying the existing tools to build the practical systems that make an impact? Maybe if you're like me, you may find the fun in leveraging the research to develop more innovative robots. Either way, it's an exciting time to be in robotics. The tools are advancing rapidly, and whether you are designing algorithms in the lab or building robots in the field, there's always something new things to learn and create. And like always, if you find this kind of content helpful, please let me know in the comments, and then don't forget to like and subscribe for more robotics insights. This is Elliot. I will see you around.